Okay, so we are going to see shunt peaking. So you can see here the capacitance may be taken at the represent to output node. I am having a coupling capacitor at the output side, and effective resistance R in the corrector side of in the output side of the amplifier. I'm going to have R and L in series. I can say it is a practical inductor. This L is going to provide the necessary bandwidth enhancement. So usually we have only resistance here. By adding L, I'm going to produce the effect of shunt peaking. Shunt peaking is going to provide bandwidth enhancement. So if you see the equivalent circuit, this will be the equivalent circuit and all the elements will come in parallel. So if you find the transfer function V out by In, so assuming that you have all the elements in parallel, I am giving a current source, I am converting it into current source, and I am measuring V out across capacitance. So if you find out V out by I in the transfer function, you get what is called as GM. GM is going to be the trans conductance of your amplifier, GM into RL. So we know that when a capacitive load is added, the gain will fall, because at high frequency the capacitance will become more and more short circuit, so the gain value will be reducing. So that is the reason if I'm going to add an inductor in series with the load resistor, the inductive component will increase the gain at a particular frequency. So how much the value the capacitor is capacitive impedance is reducing, the same amount of value the inductive impedance will be increasing. So the increasing and decreasing will get cancelled to ensure that the bandwidth is going to be increased in our network. So we are adding inductor in series with the resistance to neglect the effect of reducing capacitive impedance. So remember, capacitive incident XC is reducing with frequency because XC is 1 by omega C. So if XC is reducing, bandwidth will reduce. To overcome this, I am going to include an inductor whose inductive reactance XL will increase. So one is decreasing, one is increasing. So effectively, they will get cancelled, and our bandwidth will be constant for a longer range of frequency. That is going to be the shunt peaking. Okay, that is going to be shunt peaking, and the effective see here they have derived the impedance of the RLC network. R and L are series, so SL plus R parallel to 1 by SC. So SC, S is equal to J omega. So wherever you feel that putting J omega is very difficult, you can replace that by S. S is equal to J omega. And you get the network, the impedance of network here like this. And if you put S is equal to J omega and take the modulus, you get the impedance as a function of frequency. So you can see Z is a function of omega. So varying omega, you can plot what is Z. So this denominator term 1 minus omega square LC the whole square. Now this contributes to the increase in frequencies above the resonant frequency as well. So that is going to increase the bandwidth. So whenever you have negative terms in the denominator, it is going to reduce the value. So overall, the fraction value is going to increase. That's what they are saying. Since you have this 1 minus omega square LC term, at resonance, this term will become 0, but you still have one more term which is dominating to give you the necessary bandwidth enhancement. That is what they are saying.